Here I am presenting applications of quantum mechanics, and I am not going to give the usual textbook material that you study in your MSc classes, that is done in your classes, but I will introduce some applications of quantum mechanics that will explain the Bohm-Aharonov effect, and more than that, more interestingly, particles with any one spin called anodes. That is what I am going to discuss today, and I think that will be enough for 1 hour. Okay, now we start. In physics and in classical mechanics, what we are seeking is the time evolution, or what we are seeking is something, and if I get something, it should be possible to predict what will happen to this something on tomorrow. That is the basic culture of science. That is, that type of studies are called science. Otherwise, it is not science. We cannot predict something. That is not science. If you cannot, it should be possible to predict something, and it should be possible to verify it by experiment. Then it is called science. For example, if you consider classical mechanics, what we are doing is, the solution of Euler-Lagrange's equation or the Hamilton's equation. From that, what we are getting is, solving the Euler-Lagrange's equation or the Hamilton's equation, what we are getting is two quantities, Q and Q dot, and this Q dot is a point in phase space. What we are getting is Q dot, that is a point in phase space. Q is the realized coordinate and Q dot is the moment. And in this case, what we are getting Q and Q dot after solving the Euler-Lagrange's equation or the Hamilton's principle. When coming to the microscopic world, that is quantum mechanics, we cannot use Q and Q dot as the state, because of we cannot if you use Q and Q dot as the point in phase. This Q dot is called the state in classical mechanics. Q dot is called the state in classical mechanics. But when coming to the microscopic world, we cannot use Q and Q dot as the state of the particle, because we cannot verify Q, even after predicting this Q and Q dot, we cannot verify this Q and Q dot by experiment, because by measuring the Q and Q dot, that will change the position of Q and Q dot itself. That is the hurdle when coming to quantum mechanics. That is the microscopic world. Then the question is how we can form the state of the system. We don't know how we can form the state of the system. Therefore, we bluntly state that psi t as the state, and this state, I don't know what is this psi t is. I state that there is a state, and that is a vector. Okay. But when coming to the microscopic world, we don't know what is the state is. We cannot use Q and Q dot as the state. Therefore, we blindly state that there is a state psi t. It's a state vector. And I say that, I state that it's a vector in Hilbert space. Then the question is how this psi t, what is the equation psi t 0 to psi t by this equation. Okay. And again, since psi t is a vector in Hilbert space, it is required that psi t psi t equal to psi t0. That is equal to psi t0, and this will lead to u divided t e0 equal to 1, or equal to u t t0 units. That means u is a unitary operator. Okay. Then we know that any unitary operator can be written as equal to some exponential minus I by h cut h. Mean here h is a Hermitian operator. And if I take this h cut, since h cut has a dimension of angular momentum, if I take h as energy Hamiltonian, then there should be some time, and I put t0, t minus t0 here, so that u t0 equal to 1. Because if I consider the equation psi t equal to u t0 psi t0, it is required when timing, there is no change in time, t and t0 are equal, this psi t should be equal to psi t0. That is why I am writing u t0 equal to 1. And for that, I put a t minus t0 here. Here t is the time. If I take h as the Hamiltonian, this t is the time. Then in this case, I assume that h is independent of time. And now let us consider the case in which h is a function of time. Then, in this case, the question is how can we use this equation? If h is a function of time, we cannot say that this ht has the dimension of angular momentum. In this case, let us assume that consider the time evolution for a short time interval, that is from t0 to t0 plus delta t. And for this time interval, I can assume that h t is equal to h t plus delta t. That is, there is no so much change for the Hamiltonian. It is same for the time t and t plus delta t when t is small. Then, now let us consider the time evolution ut t0 as u, and instead of going from t0, before that I will get one more result. Instead of going from t0 to t, I can go from t0 to t1 and then from t1 to t. That means t0 can be written as u t1, u t1, t0. This is also true. That means this time evolution operator brings from t0 to t1, and this time evolution operator brings from t1 to t. By using that property, I can write, what I am doing is, I am dividing the time interval between t0 into t into small slices of width delta t, and I bring from one point to other point consecutively. That is, I can write this as ut some t0 T0 plus delta T ut T0 plus delta T T0 plus 2 delta T, etc. Then from u T minus delta T to T. Agree with that result? Then for this time evolution operator for this small slices, I can use this expression. That is, I can write it as, in this case, you should note that the times of these different operators are in an ordered manner. That is, the highest time comes in the first, the last operator, and the lowest time comes in the first operator. Then I can write this as, that is, these operators are written in a time ordered manner. That is, I can write this as exponential minus h cut h T0 plus delta T minus delta T T0 to T0 plus delta T, etc. The last step. And when we multiply, all these exponentials get added, and what we are getting is exponential minus I by h cut h. I can replace this summation of this exponential as an integral ht dt. That is, I can write time ordered exponential minus I by h cut integral ht dt from T0 to T. This is the expression for time evolution operator when the Hamiltonian depends on time. In the previous case, the expression is u t T0 equal to exponential minus I by h cut h t minus T0. This is the case in which the Hamiltonian does not depend on the time, and this is the case when Hamiltonian depends on the time. And this expression is usually used in field theory also, and this is called the Dyson expansion or something like that. Don't remember the exact name. And now comes to the different cases. And from this equation, I can get, what will happen if I differentiate this expression? For example, if I calculate IH cut d dt, we get C equal to, that is the differential of this thing, and in exponential minus I by h cut T0 to T ht dt into d by dt of exponential minus h cut integral dt. And what is this expression? It is nothing but
I think you have to put it in the left, right?
yes, we can put it in the left. Then for that I should assume that h at all times is commuting. That is, I should assume that h ei h dj equal to 0. Then only we can put. That is, for that I should assume that Hamiltonians at different times are commuting. Then we can write, otherwise it is not trivial to put in the left side. And we can write this as minus I by. Sorry, I'm mistaking it. Sorry. I'm doing this test. I by h cut ht exponential minus I by h cut integral dc.
No, I think that's what I was telling you. You have to first put the left.
That's what I. അത് സാധാരണ നമ്മൾ ഡിഫറൻഷിയേറ്റ് ചെയ്യുമ്പോൾ ഇങ്ങനെയല്ല ചെയ്യാം. ആദ്യം എക്സ്പോണൻഷ്യൽ എഴുതും, പിന്നെ ഇതിനെ ഡിഫറൻഷിയേറ്റ് ചെയ്യും. അങ്ങനെ ചെയ്യാം സാധാരണ. അപ്പൊ അങ്ങനെ എഴുതി അത് കഴിഞ്ഞിട്ട് ഇതിന് ലെഫ്റ്റ് സൈഡിൽ കൊണ്ടുവരണമെങ്കിൽ നമ്മൾ ശരിക്കും പറഞ്ഞു കഴിഞ്ഞാൽ ഒരു സ്റ്റെപ്പാണ് അത് എക്സ്പാൻഡ് ചെയ്യണം. ഇതിനെ എക്സ്പാൻഡ് ചെയ്തിട്ട് ഓരോ ഹാമിൽട്ടോണിയും ഇതിന് ലെഫ്റ്റിലേക്ക് കൊണ്ടുവരണം. അതിനെ ആ ഹാമിൽട്ടോണിയും ഡിഫറെന്റ് ടൈമിലുള്ള ഹാമിൽട്ടോണിയും കമ്പ്യൂട്ട് ചെയ്യണം. എന്നാൽ മാത്രമാണ് ഇടത്തെ വശത്തേക്ക് കൊണ്ടുവരാൻ പറ്റുള്ളൂ. ht prime dt prime. Then we get IH cut du by dt equal to h t u t dc. And it is Schrodinger equation. This Schrodinger equation for the time evolution operator. In this case, I assume that Hamiltonian depends on time. Now, okay, then now let us multiply both sides with when side is 0, we get IH cut d by dt side t0 equal to sorry, so we is missing there. Side is 0, and this is nothing but side t and d by dt of psi t equal to ht psi t, and this is called the time dependent Schrodinger equation. And you should remember that this equation, we simply derived this equation by assuming the time evolution of the state vector psi t0 from psi t0 to psi t through an operator utt0 defined by this equation. It's not defined, actually it is obtained by the requirement of the unitary, the requirement of the constant length of this psi, and simply by assuming that psi is a vector in the Hilbert space. And this equation is applicable even in relativistic quantum mechanics or quantum mechanics. In relativistic quantum mechanics, we replace this Hamiltonian with an appropriate Hamiltonian, then we get the equation called the Dirac equation and all that. This is time-dependent Schrodinger equation. And then, if this is the value of u, we can write then psi t equal to, and I am writing the t, time ordering operator, then some exponential minus I by h cut t0 to t ht dt psi t0. This is the time evolution of psi with with the time. Then, when of course when the Hamiltonian does not depend on time, we get this ht outside. We get the usual expression, that is exponential minus I by h cut h t minus t0. Now let us consider here ht. We can write the Hamiltonian as ht equal to e square. Of course, it is an operator by 2m plus u of t. Now let us consider the case in which this Vt is 0. The time-dependent potential is 0. Then we can write this integral as minus, this integral become minus I by h cut integral t0 to t e square by 2m dt dt. Of course, yes, that's correct. Then, of course, it is equal t flat. Now, the state is psi t equal to exponential minus I by h cut t0 to t to that is the basic equation that I am going to use. And now let us consider the Arnaud-Bohm effect. For Arnaud-Bohm effect, there is a, basically it is a double slit experiment, and suppose that there is a charged part, source of charged particle S, and it is coming through the slits, and an interference pattern is produced from the screen. From source S, there are two paths, path 1 and path 2, and this will cause an interference pattern on the screen. Now let us consider a solenoid is placed between screen and the slits. there is a magnetic field B coming through the solenoid. It has been found that when there is no magnetic field, there is an interference pattern, and when the current is switched on, there is a magnetic field, and this will cause a change in interference pattern. And this is called the Aharonov-Bohm effect. You should remember that if you use a solenoid like this, there is no magnetic field outside. We can assume that the length of the solenoid is very large. Therefore, there is no magnetic field inside the. There is no magnetic field affecting the motion of the charged particle, and there is no electric field outside the solenoid. Then the question is how these the magnetic field through the solenoid affect the interference pattern, and that is called the Aharonov-Bohm effect. And this again, this effect shows the realistic nature of state. In this case, we started by blindly stating the state, but it has been found that it is not a blind object. There is something in this state, and this state is affected by the magnetic field that is not causing any force on the charged particle. And that is what I am going to explain. In presence of a magnetic field, what do you mean? We know that this magnetic field is related to the vector potential by the relation L cross A, B equal to L cross A. And in presence of a magnetic field, this momentum P is changed to P minus E. Here I omit the C. Here we can assume that it is charge Q and may not be the electronic charge. Then this expression this integral become T0 to T P minus Q A 2m dt. This is equal to 1 by 2m e square, then minus Q P dot A okay, that is correct. There is a 2 here, and there is an A square term. I omitted that. I assume that this A is very small. I can omit that A square, and this is equal to 1 by 2m T0 to T P square dt prime plus then minus Q R dot is M R dot A dt. And this is the initial term here without the dt prime minus Q dr by dt dot A dt is, I am not writing this term, I am writing the last term, minus Q A dot dr. Dr by dt dot angular plus A dot dr. This is nothing but A dot dr. So okay. That shows that In presence of a magnetic field, the phase of this state gets changed by an amount Q A dot dr. A is the vector potential. Now, consider this case. And in this case, this IT along the path 1 is, there is a IT along the path 1 that is equal to exponential minus p square by 2m dt prime t0 to t into exponential minus q and dot dr from t0 to t. And for the, similarly we can write an equation for, this is for a dot dr for. Similarly, for path 2 also we can write state like this. And then what is the change in phase ongoing between the two paths? In this case, the change in phase is Q T1 to T2 A dot dr minus T0 to T0 to T minus Q T0 to T for path 1 minus this is equal to Q by using this, by inverting this integral, we can write it as equal to A dot dr. This can be written as Q del cross A dot ds. This is equal to Q B dot ds is Q into K5 is the flux through this solenoid. Then that shows that the interference pattern is affected by the flux through the solenoid. And that is the explanation of Bohm-Aharonov effect. The importance of Bohm-Aharonov effect is that it shows the realistic nature of the state. Even though there is no forces acting on the charged particle coming through the slit, the interference pattern get changed. Now, what I am going to discuss is anions. Anions are particles with anyone spin. These are called the particles that can have, usually we talk about particles, fermions or bosons. Fermions are spin-half particles and bosons are integer spin particles. And in this case, these are, of course, there are other spins, 3 by 2 and all that. In this case, anions can have any spin. There is no limit in the value of this spin, and these particles are called anodes. And it is proposed that these particles are responsible for the high temperature superconductivity. And these particles are detected, anodes are detected, and I'm going to see how the anodes comes into play. Again, usually in the linear motion of the particle, the linear momentum operator psi t equal to exponential I by h cut p, of course, dt prime, dt prime, we can write it as pt prime, dt prime, and for differentiating this, I get ih cut dt. Sorry, pressing stick. From that first expression that we have written, we can write the momentum state as I by h cut integral some x0 to x px dx, and from that we can get dx psi equal. Then we say that it is the momentum state of the particle. Similar to this momentum, linear momentum, we can write the angular momentum state as, I can write the angular momentum operator as ih cut d by d phi. Here phi is the angle. And when acts on this state, will give the angular momentum LH cut psi. This result is obtained if I write, since linear momentum, if I can write psi equal to some exponential minus I by h cut LH cut phi. From that, on differentiating, we get this expression. So that we get, on differentiating, when operated with ih cut d by d phi, I get this is the angular momentum. Now let us consider the case in which, let us consider a two-dimensional plane, XY plane, and I can assume that there is a solenoid and perpendicular to the XY plane, that is around the z direction, and magnetic field is passing through the solenoid. Now let us consider a particle going around this solenoid. Initially, without current in the solenoid, the angular momentum is LH cut. Now let us check what will happen to the angular momentum. Again, in this case also, you should note that a magnetic field through the solenoid does not exert any force on the charged particle going around the solenoid. And now let us consider what will happen when a magnetic field passes through the solenoid. And for that, again, in this case also, we can, in the case of linear momentum, we assume that P is changed to P minus, Q. Okay. In this case, also, I can assume that this angular momentum, LH cut, if LH cut is the angular momentum, is changed to LH cut. In this case, the angular momentum is caused due to the motion in the XY plane minus therefore I can write this as LH cut is changed to LH cut minus 2A phi. Here phi is this angle. This is small phi. Okay. Then what happened to the angular momentum? Therefore, when a current is switched on, this angular momentum state gets changed to exponential minus I by h cut LH cut phi minus Q A phi. I can write it as equal to, before that I write it as some L, this can be, this LH cut phi can be written as integral LH cut d phi. This integral d phi is phi. Then when the current is switched on, this expression gets changed as minus I by h cut integral LH cut minus E A phi d phi. And if you consider the last term, this is equal to, this is again Q. I am not assuming that it is electron. Integral A phi d phi, and this can be written as integral del cross A phi dot ds. This converting this, it's a line integral basically, is converting into a surface integral. And this is equal to d dot ds. If you consider a full circle, this is again equal to, if you consider about the solenoid, this is equal to, this we can convert into a surface integral, and this is equal to the flux through the solenoid. Then we can say that for a full circle, this equation becomes exponential minus I by h cut LH cut into 2 pi minus Q into flux phi. And then we can say that in presence of an electromagnetic field, the new state is exponential minus I by h cut integral 0 to phi LH cut minus Q pi by 2 pi into d small phi. I'm writing this expression because on a full circle of integration, this give 2 pi, this will cancel with this and we get this result. That means we can say that angular momentum LH cut is changed to LH cut minus Q pi by 2 pi. That means depending on the value of phi, the particle can have any angular momentum, and these type of particles are called anodes. And we can, in this case, there may not be a solenoid. We can shrink the solenoid so that it become a vortex line. And in this case also, there is no limitation on the dimension of the solenoid, or there is no restriction on the dimension of the solenoid. We can shrink it to mean 0 bit so that it become a vortex. And in this case also, there is a possibility of changing the angular momentum, and we get an angular momentum depending on the magnetic flux through the solenoid. This type of particles are called anodes. And there is a reference for this that you can read it. That is what I am going to say today, and I think it is enough. Now you can ask doubts.
No other question. I would like to ask one question.
Yes.
You started with the time ordered product of an exponent, right?
Yes.
But in between, you completely skipped that time ordered product, right? What is the justification?
അല്ല അതാണ് ടൈം എവല്യൂഷൻ ഓപ്പറേറ്ററിന്റെ ഓർഡറിങ് ചെയ്യാൻ വേണ്ടിയിട്ട് പക്ഷെ അത് that comes important when we consider when we go to the time evolution of states in field theory. അതിന് ഇവിടെ അതിന് പ്രത്യേകിച്ച് ഇതൊന്നുമില്ല.
I think
Okay.
you might have used some approximation. Otherwise, it's not right?
The time ordered product.
No, because time.
Only thing that I used is that all Hamiltonians at different times are commuting. No approximation, that's an assumption.
Hamiltonian at different times are commuting, that's what.
Commuting, yes, I am assuming it. Then only we can bring this Hamiltonian to the left side of that time evolution operator.
No, even if Hamiltonian doesn't commute different time, you can still prove that IH bar du by dt is HU, right?
If it does not commute, we cannot write it to the left side. This Hamiltonian
that's okay. That's not the thing I am saying. Still, you can write the equation.
Yes, you can write. In that case, the equation becomes UH.
Yeah. So if you want to get to UH, you should put the derivative on the left from the beginning. That's what I was telling you.
Okay, that you can do.
Because you have to write du by dt is HU, right? So you want to get H on the left, even if.
That is, I am assuming that to get the Schrodinger equation. Otherwise, I cannot write the Schrodinger equation.
Okay.
I want to ask something. These anion solutions are there only in 2 dimensions, right?
Ion solutions?
Anions are there only in 2 dimensions.
Yeah.
Not in 3 dimensions.
They are in 2 dimensions. In field theory language, they are in 2+1. They are particles in 2+1 dimension.
Okay.
And this paper, the paper on anions comes first in 1982 by Wilczek, a PRL paper. That high school student, elementary student can understand that paper.